Hi everyone, I'm going to give you a rough chalk talk on the Michaelis-Menten equation and Michaelis-Menten kinetics. And essentially what I'm going to do is show you a derivation of the equation, but I'm not going to go through every step. I'm just going to go through the main brushstrokes, the thinking process, and the key highlights on how to think, the way your mind can possibly go when you're figuring out on your own, okay? So the key thing is this equation here, all right? Enzyme plus substrate goes to the enzyme-substrate complex, right? And then it dissociates into the product and the enzyme again, all right? Now, everything Michaelis-Menten does is models this process. But this process is complicated because you have several subreactions that are happening at the same time. You have E plus S going to ES through this rate K1, little k1. You also have the back reaction of ES going to E plus S through K minus 1, all right? And then you have ES dissociating into the enzyme plus the product, which is described by the rate K2 here. And we're going to assume that this back reaction does not occur. So we have three reactions to model all in one equation. And that's what we're going to try to do. We're going to try to describe this process with one overall modeling equation. So the first key thing that you have to keep in mind is that we're going to take into account certain assumptions. And those assumptions will allow us to do math. And math is simply a tool to help us describe reality. The first assumption we're going to do is the rate of ES formation equals the rate of ES dissociation. So what that means is that in the back of my mind, I'm trying to keep this level of ES, the enzyme-substrate complex, constant. And the reason why I want that constant is because it simplifies things, all right? If I have this constant, then I could talk about these rates going forwards, backwards, and forwards again, and it will be more meaningful because this, which is involved in all of those three processes, needs to be held constant, right? So I'm going to say the rate of ES formation equals the rate of the ES dissociation, right? Which is this guy right here. Now, what that allows me to do is that allows me to have an equal sign here. Because, see all these red equal signs that go down? Okay? See these red things right here? If I didn't have that assumption, then I wouldn't be able to set everything on the left side equal to everything on the right side. Okay? And so you always have to start with some sort of assumption. So the rate of ES formation is described by any of these arrows that is going towards ES. And there's only one that's going towards ES, and this is K1. So this equation describes the rate of formation of ES, all right? I'm not going to go too much into it right now. Now, the rate of dissociation is described by any of the arrows going away from ES, such as this one and this one, all right? And that's why I have two expressions here that I'm going to add to each other that will represent the rate of ES dissociation. Now, because of this assumption, I could set those equal to each other. Then, at this point, there are a few key substitutions, all right? One of them is that I'm going to replace this enzyme with E total minus ES. Because of all the total enzyme present, there are two possibilities. The enzyme could either be, let me go up to the original equation. The enzyme can either be bound up in ES complex or it can be free, right? So therefore, if I wanted to replace this term, all I have to do is E total minus E minus S. E total minus ES, sorry. So, all right, now I'm not gonna spend too much time describing what's happening, but essentially what I'm gonna do is I'm gonna try to isolate ES. So this whole area down here, okay, I want you to look at the math more carefully, but essentially, look what I'm doing. I'm distributing here, and I'm making ES by itself so I could add it to the right side right there. See, this is going there. In the meantime, I'm factoring out the ES, and I'm trying to make it by itself, all right? I want ES to equal something. And now you have to ask yourself the question, why am I doing this? Why am I manipulating the math? Well, the reason why is that, again, we're trying to model this process right here with a mathematical equation. The problem is, not only do we have to model it, we have to be able to measure it. So ES is hard to measure, okay? So if something's hard to measure, but it still matters, then you try to re-express it in terms of things that you can measure. So this ES right here, I'm going to try to replace it with something that means ES, but in terms of something that I can measure. So see this arrow right there? What I'm going to do is tell you how this ES can turn into V naught or whatnot, okay? So now, pay attention to the pointer. So let's go back up here, all right? So the ES dissociates into E plus P, and that's going to be rate limiting, all right? In other words, for this whole reaction, the whole yellow reaction, the slowest part we're going to assume is the breakdown of the ES into the product and the enzyme, okay? So if that's rate limiting, then that means that the whole thing depends on this slow guy. So essentially I could say the whole rate of this big equation is represented by V naught equals K2 times ES, right? So K2 is the slow person in the line, so the whole thing is going to be K2 slow, right? So notice how it's written in terms of ES right now. But as I said earlier, it's hard to measure. It's hard to measure ES. So you need to express it in terms of other more easily measured variables. So that's what this this loop right here is. Now, check this out. There's a really cool assumption right here that you have to understand. Now, this ES, right? If you isolate it, you end up with this equation. However, I could set ES equal to ET. I could set ES equal to ET. And you can only do that if you know when that is true. And the total amount of enzyme available is bound up in the enzyme substrate complex at Vmax, at the maximum velocity, right? So when you have all hands on deck, there are no free enzyme. Therefore, I could set ES equals to ET. Now, keep that in mind and try to think why that is true. So once I do that, I'm going to replace, see this ES here? This ES just equals ET at Vmax. So therefore, I could take this expression and put it in there. So what I'm going to do is I'm going to replace it V naught over K2, all right? And you end up with V naught here, okay? So I skipped a step, but basically I multiplied both sides by K2, and the K2 got multiplied into the numerator of this side, right? And it turned into Vmax, which means that K2 times ET equals Vmax. K2 times ET equals Vmax. Where is that coming from? Go back up here. K2 times ET, which is the same thing as ES, only at the maximum velocity, all right, equals Vmax, because it's rate limiting, okay? So that's another leap. So now, finally, we have our Michaelis-Menten equation. V naught equals Vmax times S divided by Km plus S. And remember, this term right here is going to be Km, okay? And you can go through the math. So anyways, that's the first slide. Now I have 3 more slides, okay? So let's go to the next slide. So, all right, now that we accomplished this derivation up here, what are you supposed to do with it? What's the point of, what's so special about this, right? Why are we doing that? Well, now what? So the whole point of this was to model reality, remember? So we have an equation here, and we want to see if it works. It's like you built an airplane, let's see if it flies, all right? And the way we see it flies is if we look at our data, and then we see how well that this equation describes the data, all right? So let's look at 2 situations, all right? So here's our data. Let's test number 1, okay? The data is the velocity on the catalytic velocity on the y-axis and the amount of substrate on the x-axis. And you notice when you're in the lab, you'll see that the velocity increases really fast and it tops off and you hit the Vmax up here, right? So when S is really small, we're looking at this area down here, right? See, here's S, here it's where it's really small. Now, back here it looks kind of linear, right? So this line, this derivative is linear. So in other words, let's go back to this equation, right? When s is really small, it's around 0. It's around 0. And this one's around 0, okay? So both of them are around 0. So basically what happens is they end up falling out of the equation, and it becomes Vmax over Km, and that's a linear equation. And it just so happens that this looks linear right there, right? So it works. This thing can adapt to this graph at the concentration that we tell it to, right? So what happens if you plug in a high amount of substrate, right? So then you have, if this number is really big and this number is really big, the Km stops mattering. So for example, like if I put 1,000,000 for S here and a million for S in the bottom, and Km was just 1, it'll be 1,000,000 over 1,000,001. So the 1 doesn't really matter the more S gets larger. And that is accurate here where you have a lot of S, a lot of substrate, right? So in other words, our equation is adapting to our graph. It's adapting to the data that we have. So therefore, the Michaelis-Menten equation has predictive value, okay, at both ends of the spectrum, all right? So in other words, down here, I forgot to say, look, all right, the velocity is more described by the Vmax when S is high. So in other words, it's working. Okay, so wow, the Michaelis-Menten equation maps on well to the curve, and it has predictive value depending on the S. Okay, so now let me just tell you, how did I decide to test it that way? How did I decide to make S big and S small? All right, well, here's a little hint. So whenever you get an equation that looks like this, so remember, look at this here. V naught, or who cares what it is, something equals, and you have two terms that are the same on the numerator and the denominator, but the denominator has something added to it. So I could say like hot dog divided by hamburger over hot dog. Any equation that has hot dog divided by hamburger over hot dog divided by hamburger plus hot dog, then that's asking you to look at the substrate, to manipulate the hot dog concentration to see what it is when it's high and when it's low. So when this is really, really high, the hamburgers don't matter anymore. And when this is really low, then the hamburger starts mattering, all right? It starts exerting more of an effect. And I made another YouTube video on the Michaelis-Menten, how to explain Michaelis-Menten to a kid, all right? So check that out. All right, let's go to the next. Okay, now, this is how it's going to be tested in your class. So basically, check this out. Here again is the Michaelis-Menten equation, right? The problem with this is that it is difficult to compare different enzymes by looking at the curved graph. So it's better, and there are other difficulties too that I don't remember. But basically, what we need to do is we're going to reformat this graph into something called the Lineweaver-Burk plot. And what that does for us is it makes it visually more easy to work with. And all you need to do is take the inverse of it, okay? So you take the inverse of the left and the right side, and you end up with this expression. You distribute this quotient to both of the terms at the top, and you cancel the s's, and you end up with this equation here. Now, the key thing here is that is just y equals mx plus b. Y equals mx plus b. So what that does for us is that it enables us to graph it. So let's just put this as the y-axis here, and this as the x-axis, right? And you end up being able to graph it. So the two key points you want to pay attention to are the x-intercept right here and the y-intercept. And so if I gave you a number here, you should be able to calculate Vmax because you just have to take the reciprocal of it. If I gave you a number here, you should be able to calculate Km because you just take the negative reciprocal of it, okay? And here you have, back to middle school algebra, this is how you calculate the x-intercepts, all right? For the x-intercept, you just set the y to 0 and solve for x. For the y-intercept, you set the x to 0 and solve for y, all right? So chew on that for a little bit. All this gets you are these 2 points right there. right here. See? Okay, now we're going to take it one step further. So the whole point of this is to be able to talk about inhibition, right? So check this out. You have competitive inhibition where the Vmax stays the same, but the Km decreases, all right? The Km changes. So the slope changes in a specific way, and you should be able to recognize that, right? So then you have non-competitive inhibition where the Vmax decreases, but the Km stays the same, all right? And don't be tricked by, just because this goes up, it doesn't mean that Vmax increases, it decreases, and I'll show you why. So here's a little summary here. So here's the x-intercept. If it goes to the left, that means Km decreases. If it goes to the right, Km increases. Whereas if the dot here on the y-intercept goes up, Vmax decreases, which is backwards, because it's the reciprocal of it. And then you have it increases as you go down, all right? And I have some more math here. There are some expressions that model the inhibitor, but I'm not going to go into that right now. So anyways, what do we talk about? All of this was coming from the Michaelis-Menten equation. So because